Hello everyone. In this session, let us discuss about visualizing the hypothesis space of a gradient descent. So this is how the hypothesis space will look like. So here you can see we are having weights W0 and W1. Instead of taking a single weight, we are taking two weights here, W0 and W1. And here you can see the output function also. And as we have just seen in the earlier session, always the gradient descent is a parabolic one. So whenever you are applying a gradient on the output function, the error you are getting in terms of a parabola, right? So here the axis is W0 and W1 represent possible values for the two weights in case of a simple linear unit. The vertical axis is indicating the error E relative to some fixed set of training examples. And the arrow, so this arrow, so this is showing us the depth. This arrow shows the negated gradient at one particular point, indicating the direction in W0 and W1 plane. And it is also showing us where the steepest descent we will be having in the error surface. So that is also shown. So here this arrow is showing us the depth. Okay. So in the earlier session, we have seen a simple parabola. So here we have taken multiple weights. So multiple parabolas we are obtaining. And along that, we are measuring the output also. Okay. So here, the error surface must always be parabolic with a single global minimum. What is global minimum? The point where you are reaching to the flat surface. So that is our global minimum. And the specific parabola will depend on the particular set of training examples that we have. So what will be the shape of the parabola is dependent on the weights that you are taking. And the gradient descent search determines a weight vector that minimizes the error E by starting with an initial arbitrary weight vector and repeatedly modifying it in small steps. So this is what we have seen in the earlier session. If you have not watched the earlier video, please go back and watch that. This will be very clear to you. At each step, the weight vector is altered in the direction that produces the steepest descent along the error surface. That is what we have seen. Our gradient will not only give the value, but it will also give us the direction. When we calculated the mathematical value, so it has given us a negative value. So that means it is coming down. And this process will continue until the global minimum error is reached. So that means your parabola is like this. So you have started at some highest point. So if your ball is here, your output is here, right? So then when you have reduced the step size and again you are measuring, suppose initially let us think that I have taken a large step size. Let me take a large step size. And then coming down, we will be having a very smaller step size. Incrementally, we will be taking smaller and smaller step sizes until I reach to a global minimum. Okay. So this is my global minimum. So why the term global? So earlier we have seen until a local minimum, right? Why we are using the term global minimum is, suppose my surface is like this. Okay. So here if you observe, instead of having one steepest descent, I have multiple. So now all these points I will be calling as local minimum. Among all these, whichever is the steepest one. So here this is the steepest one, right? So this we take as global minimum. So we are continuing this process until a global minima is reached. Okay. So this is how we will be visualizing the gradient descent search space. Hope you enjoyed the video. See you in the next session with the derivative of gradient descent. If you enjoy this thoroughly. So please do like, share, and subscribe. Thank you.